What is the vanishing and appearing sources during a century of observations really about? Well, let me be clear. It's about ET. We want to find ET. And ET and extraterrestrials have been the motivator for our searches. Although we don't only do searches for ET, we have a little bit of this policy of that whatever we find, we will publish. Even if it's conventional astronomical phenomena, we will publish it. So traditionally, there have been very few ways to look for ET. And people have been thinking, so why should we look for them? Because we don't know if they exist. We don't have any signature, nothing that would indicate that any other civilization is out there. Well, I'm just going to remind about that there are like 200 to 300 billion of stars just in our Milky Way, our own galaxy. And there's about 400 billion galaxies just in the observable universe. And we know that like at maybe as much as 50% of all stellar systems have our Earth-like planets orbiting. So we have very many candidate planets that could be hosting some type of civilization or some more primitive life. So I think there are good reasons to look for ET. Traditionally, most of these searches have been done in radio. I don't know if many of you have seen this movie called Contact. That is a wonderful movie about a researcher that is looking for ET with the radio telescopes. It's a great method, except for that it's very, very costly because you need to search for, or you need to observe the same star during years and years of time. And you don't know which one of all these stars that you're looking for is going to actually host that life, that intelligent life that could be transmitting clear-cut radio signals. Now, there are other ways of doing that too. For instance, anomalies. And when you search for anomalies, you might actually not find ET, but you might find something else. Let's say when one first discovered the first quasar, is the 3C273 that is here depicted on the image in the middle. So a quasar is a supermassive black hole that is accreting lots of gas and emits lots of luminous, very strong light from the center. And when one first saw it, one thought it was a star, and then one took a spectra of the star and said, something is wrong with this star. This star looks like it's not in our galaxy. And this is how finding an anomaly led to a really important discovery. We discovered these super accreting black holes in this way. So that's one example. Another example is that when one discovered the pulsars in astronomy, one first thought, oh, this looks like aliens, someone said, because it looks like periodic radio signals coming from these weird stars. And well, one discovered a new type of objects. It wasn't ET at that time either, but it was super interesting and it led to a Nobel Prize. And another object you might have read a lot about in the media is Tabby star, which is a star that has been doing some weird, very slow type of dimming in the last 100 years. And so far, nobody knows what is causing this dimming, really. One thinks it's some type of dust, but when it was discovered in 2016, the first thought was, could it be some type of megastructure, some big alien structures like that are like making the star dim? We don't know yet, but we are still going to find out. No signal of ET has been found there yet. And finally, I think many of you have heard about the Oumuamua object that has been figuring a lot in the media in the last 2 years, where some people propose that this could actually be a space rocket and not a natural object. And we again ask, is it aliens? It might be so that it's aliens this time, or it will turn out to be some type of new anomaly that we will learn from. So looking for anomalies is a really good start. And even if we don't find ET, we can find something else. So now in the Vasco project, we are interested in anomalies, but we are not only interested in anomalies. We were thinking about that. How about if you look for something that would be absolutely impossible? Something that would look like magic in the eyes of us physicists, that we would say like, no, that cannot happen naturally. And maybe we can target our searches to look for this magic in big sets of data. Because if you find something, you either find a new astrophysical phenomena that will kill some dogma and you're happy, or you actually might find that technology that you're looking for. And this is the basics for the Vasco project, where we are actually focusing our searches on vanishing stars. Because we know that if a star dies, either it like explodes in a bright supernova, or it's during billions of years fades into a white dwarf, but it doesn't just vanish. So this is how the Vasco project actually works. We have an initial data collection. We're comparing images from the 1950s, before any satellites were in the sky, when our sky was completely without any human contamination. We compare these images from the 50s with images from how the sky looks today. And we collect all this data, we compare the images and the catalogs, and we see, has something vanished possibly? And with that, we are actually finding a lot of natural objects, natural so-called transients. Transient is an event that is very short in astronomy, let's say a supernova or so-called gamma ray burst, something that lasts for just a few minutes and you see it. So we collect a lot of natural transients by doing this. And we also collect a lot of, or we expect to collect a lot of rare transients, let's say quasars that are having some type of variability that can last for years. So these are the natural things that we collect. But we also hope to find so-called Dyson spheres around stars, where, let's say, a civilization might have built a shell around a star and gradually it dims. And we hope to find maybe some vanishing star that has been manipulated through stellar engineering, or even appearing stars. I'm very proud to say that this image with the green little aliens was actually published in an astronomical journal. I never expected it to happen, but we got it published with these little green aliens. So yes, this is what we all are looking for. And we collect all of this stuff, and we hope that to eventually find this wonderful signature of ET. So, does it give us some other kind of scientific opportunities? Yes. There are some people who say that, according to a few theories, certain stars within a very defined mass range might collapse directly into black holes. Nobody knows if these theories are correct, and we know that it's extremely unlikely that it will happen in the Milky Way. So if we find something like that, it will be equally cool for us as well, because that would bring a lot of light to supernova physics. And as I also mentioned, the quasars, which is my other research field, and these supermassive accreting black holes, one can also find some of them that show long-term variability, extreme long-term variability, and these things would be fantastic in order to actually know, like dismiss and reject a lot of current theories about the engine of the quasars, because I can say that there's a very poor understanding of the engine so far. So even if we find this, we will get something nice out of it. So our first official paper, there was one more earlier, but the official paper was in 2020, and we found 150,000 candidates just based on the text catalogs. And the problem was that with these 150,000 of images, one had to look through them one by eye. Looking through 150,000 images by eye is not an easy task. I looked through 24,000. It took 3 months, lots of chocolate. I got one dioptry more in my myopia. And yeah, and when I looked through 24,000 of objects, I found 100 unusual transients that were very short. I did not find any clear candidate of a vanishing star so far, but it was an interesting start. Here I show examples of the things that I found when I looked through the 24,000 of the candidates. You see here a beautiful object in the image from the 1950. This is a red image, and it's not there later. This is another time in the 80s. Here we have it in 2005 and 2015. So you only see that event in the 1950s. Here's another example. You see something here in the 50s. You don't see it as much, but it still is seen in the 80s, and you don't find anything later. And hundreds of these type of events were found, and we think that they are natural astrophysical phenomena, although we don't know yet what they are because we need to do follow-up observations. And to explore all the other ones, we started up a citizen science project, and that has been done together with machine learning scientists, image analysis researchers, actually game developers, and astronomers. And we have introduced the first 150,000 of candidates that were purely based on the texts. So here is how it looks. And if you want to see the citizen science project, you can go here. It has a random number generator currently that is spitting out a mission number. And there's also an AI. And eventually the AI is supposed to replace the random number generator once it has trained enough on enough many cases. And in order to do the projects even more interesting, we are collaborating with several schools, institutes, and amateur associations in African countries, in particular in Nigeria, Cameroon, and Algeria. And we hope to implement the Vasco project as a part of the education there, so that we know that even if we don't find ET, we hope that we can inspire many of these young African astronomers into research. So that's a side thing we do. So far, out of the 150,000 objects, we have 114,000 classifications. You can see here a timeline when the project started last year. It started very slowly. Then things started being a little bit more visible. Then I gave a talk at the SETI Institute, and you see a big peak here. Well, right now we have 1,800 candidates roughly that are marked as vanished that we have to look through and double check. So that's the status of our citizen science project. We actually also have automatized searches, and by the end of September, we will have an automatized answer to whether there are any vanishing stars. So it's all happening right now. All the results are coming in the last months, and it's very exciting. So during this project, we actually found something really weird. And that is actually what I mainly would like to tell you about. So this is a paper that was published 2 months ago in Nature's Scientific Reports. The paper got a lot of both unusual attention, we can say it like that, due to several factors. There were some canceling on social media, and there were some very excited astronomers. It really lifted all kinds of emotions. And it's called Exploring 9 Simultaneously Occurring Transients. I'm going to show you an image. You see here 9, well, it's basically 9 objects. It looks like normal stars. Let me show a little bit clearer. Like if you look at the light profiles of these objects, the black one is of a typical normal star, how the brightness falls off as a measure of the distance from the center. And all these objects just look like normal stars. Now, if you have a very careful look, you're going to discover that that there's a tiny problem. And that is that among these objects, they were there in 1950. They are no longer there in 1996, and this is a small region of the sky. I actually, unfortunately, included some digitate. This is actually, I haven't marked it here, but this is not a real star, unfortunately, and neither are those. These are digitate scanning artifacts. I forgot to mark them. Sorry for that. Anyway, 9 of these objects are there in 1950, but not in 1996. And if you start comparing, you see that 6 days later, these 9 objects weren't there. And if you look at it half an hour earlier, they also weren't there, which is really, really weird. So we first, as a first intuitive exploration, we used the Gran Telescopio Canarias, which is a 10.4 meter telescope, trying to see, okay, if there were stars there, Have they possibly vanished? Is there something at the spot? We got really deep images. For some things, we found something on the place, for others not. And we kind of looked at it with this GTC. You see here the much higher resolution images that are modern, 70 years later. And we kind of concluded that maybe those that had some kind of counterparts were just chance projections. It could be that they were just, if you have a really high resolution images, you will always find some background stars. It doesn't mean that they are physically connected. So we suddenly have a problem. What are these 9 objects that we see? And we have taken a look at astrophysical reasons, and there is absolutely not a single astrophysical explanation to having so many of transients that happen in a small region of the sky at the same time. There's just no way, pure astrophysically, because the density is too high. And so we started looking at different instrumental issues. We were thinking, could it be that the images have a different spectral sensitivity? But no, because we could compare it with an image taken with the same instrumentation 60 years later. We were wondering, could it be some type of ghost image? No, because the stars had just too perfect brightness profiles. Could it be a double exposure? We did a few tests, and it seems we cannot exclude it, but it seems quite unlikely, or very unlikely. Emulsion problems, again, we have the problem of that all these objects have very star-like profiles. Now, again, it should be 9 star-like defects, not 12, because we found out later that 3 out of 12 were scanning artifacts. Cosmic rays, they are not a problem for photographic plates in the same way as they are for modern CCDs. So we started excluding one reason by another, so then we started getting more desperate. Our referee asked, could it be that someone sneezed on the plate? So then I had to open some COVID-19 articles, look at the profiles of water, saliva, and you see that saliva does not give perfect round shapes, as you can see here. They give elongated forms and all kind of things, different distributions of sizes. No, nobody sneezed on the plates. So we now call it unknown contamination. One hypothesis that we had is that it could be nuclear fallout, because nuclear fallout can give actually these beautiful round spots on X-ray film. Now, I don't know if the red emulsions from the 1950s were sensitive to the X-ray film. There's just one problem. In the place where in the region, it's called near the Palomar Observatory, there were no nuclear bomb tests. Actually, in general, in US, one didn't do any nuclear bomb tests in that year. And there were no official bomb tests between 1949 to 1951. And so one can, of course, question whether the official lists are complete or not. And the second problem is, of course, also that we are seeing more of these events in a confined region of the photographic plates, while maybe this contamination from nuclear bombs would have been all over the plates. So I don't know. We call it that it might be some unknown type of contamination. However, we also started thinking of a different possibility. If you would use exactly the same instrumentation today, and same instrumentation, and look at the sky, you actually could find this type of multiple transients in a small region. You would find it quite often. And why is it so? Well, because today we have a lot of satellites, a lot of space debris. In fact, most of the times when you think that you observe a very fast flash on the sky, it's just a solar reflection of a satellite or debris. And that comes from it can be small objects, even just centimeters or tens of centimeters in size, and that create these very fast transient-like events. However, no glint should be observed before 1963, when the first satellite was launched high enough to reach a geosynchronous orbit. Also, the first satellite was in 1957. So theoretically, we shouldn't be able to observe this kind of events, because our image is from 1950. we still ask the question, and which leads us to the kind of conclusion that we're either dealing with some type of unknown contamination that we couldn't at all pinpoint, or possibly we are observing something that could indicate that some type of artificial objects in high orbit already in 1950. In order to test the latter scenario, we're going to look for this type of image is something that would be a much clearer signature of metal or glass or something reflective in these images in 1950. And we are doing these searches right now. I estimate that we will have our answer within a few months, since we already have all the citizen science results and all the results from the automatized sky scan. Since all of this is already in progress to be finished, it will just take a few months extra to search for these very clear signatures of metal in high orbits. And with this, I think I'm finishing the talk. I have shown you our latest results from the Vasco projects and our ongoing mystery with the 9 simultaneous transients. And for people who are excited about what astronomers can do with UFOs, I have also recently joined Avi Loeb's Galileo projects that some of you might have heard about, where they are planning to do a data-driven and observational approach to searching for UAPs and UFOs. And I finish my talk here. Thank you.